So notice, if you compare A, B, C here, which is naphthalene, and naphthalene has three resonating structures, then how do we decide which one is a perfect or better or more stable than the other? Check. If you compare A, B, C, out of these three, have you noticed something that this ring is also a benzene form? This ring is also a benzene form because pi bond is shared between both the rings. But here, if you notice, this ring is benzene form, but this ring is not benzene form. Same logic, right hand side, the structure is benzene form, but the left hand side is not benzene form. So usually the one which has more number of benzene form, that is always going to be more stable. Hence we can say A is more stable than B than C. Why? A has more number of more number of benzenoid benzenoid rings. So this is what you will be noticing henceforth. So if you had more number of benzenoid rings, the stability of that particular compound will be more. Okay. In fact, you know how much it will influence here, because A contribution is more than B and C. So if at all I write the hybrid of the same, so do you remember how to write the hybrid structure? So here, this is naphthalene. On the naphthalene, usually we write the hybrid like this, correct? Because we show that the double bonds are delocalized in all the places. Now imagine if at all I gave the numbering for all the carbons here. Let's say 1 to 6. I've named it for only one ring. Now one thing, can I say that, out of A, B, C, the most contributing factor to hybrid is A, right? A is most contributing. Now remember, the hybrid will always listen or mimic. Hybrid will listen or mimic the properties which are contributing the most. Out of these three structures, which is contributing the most? A is contributing the most towards stability. In that case, the properties of this naphthalene will also have similar properties as that of A. So can you notice in A here, if I write the same thing in terms of numbering, so check out what do we get? You will get this as 1, 2, 3, 4, 5, and 6. So now from 1 to 6, if you compare here, so I can say that 1 to 2 holds a double bond, 2 to 3 holds a single bond. Therefore, right, so therefore we can say C1, C2 bond length, okay, C1, C2 bond length, that has to be lesser than C2, C3 bond length, isn't it? Bond length will be more there. Likewise, if you have C1, C2 bond order means, more of double bond character here. In this case, more double bond form. So, more number of bonds it has as compared to that of C2, C3, which is having bond order like this. So, do remember this part. So, how uh, we have bond length and bond order defined. So, I guess the naphthalene case is clear, everybody. The next one, stability, is easy. Here you can see there are no pi bonds. Here there is one pi bond. So more the number of pi bonds, more is the stability. So B greater than C. B has B has more number of pi bonds. I guess all of you have written the 10th and 11th, everyone. Please check. Come to 12th one now. So we need to figure out, this was a JE question which was given A, B, C, D, little old question, old JE question. So in this case, it has been asked like which one will have more amount of uh, let's check out which one has more stability in these cases. So how would we get that? So please do check here. So first, check out number of pi bonds. Two pi bonds here, two pi bonds here, two pi bonds here, and two pi bonds. So you can't differentiate anything with respect to number of pi bonds. Then check out the I mean, the charges. Who is carrying the charges? Whether you have more plus electronegative charges carrying negative charge, electropositive carrying positive charge. So that should be the criteria you should look out for. So out of that, if you notice, the D qualifies the better. So in case of D, oxygen, which is more electronegative, is carrying negative charges, and carbon holding positive charge. I mean, carbon has less electronegative and it is holding positive charge. That shows relatively more clearer in D. And thereafter, please notice the negative part and the positive part will always attract each other. So if they are closer by each other, their chances of strong attraction. So hence, you can have A has the next stability order. Next. If you notice, plus and pluses are repelling each other. That means this has to be the least stable form. So while here plus and minus strongly attract, here also plus and minus attract, but not as good as this one. Hence, it is supposed to be C and then compared to that of D. Sorry, compared to that of B. So this is the order of stability. Everybody clear? So multiple factors. The first factor we got here is based on number of pi bonds and who is carrying the positive and negative charges. Next, check out 13th one. Which can't be resonating structures? Which of these cannot be resonating structures? If you remember the one rule which we discussed, that the number of pairs of electrons in resonating structure should always remain same. Have you noticed? This is one pair. A pi bond is a pair. So one pair and one pair. So there are two pairs. So throughout the resonating structures, it should always maintain two pairs. So you can see one pair here, one negative charge here. So that means these two are different pairs. Next, minus charge and pi bond. So this is one pair, this is one pair. But here there is one pair and two unpaired electrons. The dot dot means two unpaired electrons. Hence, we can say ABC are resonating structures. D is not resonating structures. Resonating structures. Clear? No, on the basis of basic pointers of resonance, that what are all the factors you need to measure to check out the stability. There is another important part of measuring the stability, that is about checking whether there is an equivalent resonance available or not. Equivalent resonance is appeared when you have same structural features, and that's going to be defining its stability. So same structural features. If more number of equivalent structures are there, that means it is more stable. For example, benzene, like I said, as per NCRT and in generally also, if the number of resonating structures are asked, always go with two. So we assume that these are the two forms, calculate structures are the two forms which look exactly same. So the other forms are least contributing. This one are least contributing resonating structures. So these two are most resonating structures, and because it has an equivalent resonance, we believe that brings more stability to benzene. Okay. Likewise, this is called formate ion. Okay. So this is formate ion. So you can see HCO minus. So that is in equilibrium with HCO minus. And how do we write the hybrid? Because the structure looks exactly same here. So we can say the electron density is moving between these two CO groups. And here it will start gaining delta negative, and here it will start getting delta negative for some time. Okay. So that will be the format time. Okay. So here also the contribution will be 50-50 percentage. So that means if this is 50% contributing, this will also be 50% contributing. The next one is acetic acid. Acetic acid is the same thing here. Both of these are equivalent resonance. So we can say the resonating structure will look something like this: delta minus and delta minus. Finished. Now imagine this one. If at all I ask you, compare the stability of acetate ion and phenoxide ion, PHO minus. PHO minus is phenoxide ion. So if you compare A to E, you need to check which one is more stable. First, judge between A to E. A to E, which one is more stable? And this one I'll call it as F. Okay. Now have you noticed something? A is a benzenoid form, and so does one more structure we have. Okay. Where is it? Here, B. A and B are equal contributors. So we can say A and B are equal contributors, and it has more stability as compared to that of, you know. Now your question should be, sir, how do we decide between D and E? In D and E, notice this one, the negative electrons are more closer towards oxygen, right? So there will be attraction, sorry, there will be repulsion of these two groups. Therefore, D will not be as stable as that of C. Hence, we can say A and B. Thereafter, we can get this as, sorry, E, and then we'll have C and D. This is the stability order. And if you compare the least stable one, so what does this mean? See, this is what something you need to understand. Phenoxide ion is a non-equivalent resonating structure. So this is non-equivalent. Okay. While acetate ion is equivalent. Only if you know that equivalent resonance is more dominant than non-equivalent resonance. That's the reason why F is greater than rest of them. You do not need to worry about checking how many number of conjugate structures one can give. So as long as equivalent versus non-equivalent, the comparison is very simple. Equivalent will always be more stable than non-equivalent. Done? So that's the importance of equivalent resonance. It will overpower rest of the any non-equivalent cases. Next one being extended conjugation. So if you notice the first case itself, if you compare, how does it look like this? Now in here, if you notice how the resonance is taking place, you can see the pi bond can move on to this position. This pi bond can move on to this position. So which brings it double bond O minus and double bond here and plus. Okay. This is how you can get. Again, this minus can be pushed here. Pi bond can be moved here. So we will get this as double bond and O minus. This is the resonating structures for this case, isn't it? So we will have two resonating structures of it. So second case, if you notice the second case here, we would have double bond, double bond, double bond O. So please do check. Now notice if the resonance happens from here, the pi bond will be pushed, this bond will be moved, which means we can have this as double bond with O minus. Okay, so here we will have this compound. Now, have you noticed that this is the only resonating structures we can have? But in the case of this and this, if you compare, this one has more number of resonating structures while the second one has only one resonating structure. So from there you can clearly notice that the first one being more stable compared to that of second one. Why is that? The first one you can see the pi bonds are in conjugation throughout the rings. But here when this pi bond is being making conjugation, this pi bond has no role on it. So it will remain at the same position. And such kind of conjugation is called as, if you compare this extended conjugation part here between these two, you can see this does not have any extended conjugation. This has the extended conjugation. Hence, stability wise, if you compare, so we can say that if this is A and B, definitely A is far greater than that of B. So this is the stability. Extended conjugation will always bring a lot of stability. So same logic we can apply even on the second case. If you notice this one, if pi bond is shifted here, this pi bond can be shifted here. In that case, this pi bond has no role, right? So this pi bond has no role because resonance is happening here to here. So this is not being able to involve in resonance. So likewise, if the resonance is happening on this right side here, so this pi bond will be ignored. So hence this is a split conjugation or cross conjugation. While B is a straight conjugation from here to here, here to here, and here to here. Hence, if you compare to that of stability here, we can say B and A is the stability order. Okay. Now this we have done in chemical bonding. Anyways, I'm trying to repeat it once again. Suppose if you have, you know, equivalent resonating structures given, in the case of equivalent resonating structures, then we can say like this, we will have these three. Now, if you have to compare what is the charge on all of them. So first, you need to check. Now, this is how the resonance is taking place. Out of that, if you notice something, here it is zero charge, here it is -1, -1. So three resonating structures, out of which, how much is the charge? -2/3. So this is going to be -2/3, -2/3. And if you compare the bond length here, so there are two bonds here, I mean bond order here. So two bonds, one bond, one bond, total four bonds distributed across three structures. So four border. I mean 4 bonds distributed across 3 structures. Everybody clear how we got 4 by 3? So 4 by 3 is the bond order. So use this concept, everybody. Try to redo the second one. We have done it already. So please do check. Check out the bond order and then comparison. We discussed this already about the stability part. Stability part we learned for naphthalene A is more stable than B and C. This is based on number of benzenoid forms. Benzenoid forms. So how many benzenoid forms we have? Okay. Now let's come to the bond order, everybody. This is the hybrid structure like this. This is the hybrid structure of naphthalene. So if I go with the numbering 1, 2, 3, 4, 5, 6. So now I want you to compare C1, C2, C2, C3, correct? So in this particular order, we need to figure out what will be the bond order in all the cases. So please check. Between C1 and C2, have you noticed something? C1 and C2, the most contributing one is which one? Most contributing one is structure A, right? Because it has two benzenoid forms, two benzenoid rings. So between these two, correct, here we have one sigma bond. Here there is one pi bond and one more sigma bond here. So I can say there is one sigma bond which is always there. One sigma is always there between C1 and C2. And then if you compare these three structures, 1, 2, and 3. In these three structures, how many times a double bond is repeated, everybody? On this line, how many times double bond is repeated? Only one time, that is on B. So out of three canonical structures, we have pi bond repeated only one time. Hence, we can say one pi bond divided by three resonating structures. 3R means three resonating structures. Hence, it is about 1 plus 1 by 3. These are the amount of bonds we have, which means it is 1.33 bond. So what is the bond order between C1 and C2? 1.33. While what about C2 and C3? C2 and C3 here between these two. So now let us compare that line. This line, and this line is what you need to compare, everybody. So in here also there is one sigma. In all of them there is one sigma. And then how many number of pi bonds we have? Can you see there are two pi bonds across three resonating structures, and that is equal to 1 plus 2 by 3, which is 1.66. So the bond order between C2 C3 is 1.66. Same way, C3 C4 will remain 1.33, C4 C5 will become 1.66. Okay, this is again an important JE question, everybody. What is a bond order of different carbon atoms in naphthalene? So naphthalene always carries two different bond orders. One is 1.33, the other one is 1.66. So I guess this question is clear, everyone. Next. Notice what is resonance energy. Okay. This is also called stabilization energy, wherein we expect the energy is released when it is undergoing resonance. So in short, it is the energy difference between the most stable canonical and hybrid. Most stable canonical means resonating structures. Out of the resonating structures which were possible, the one which has most stable form. So that most stable by high with respect to hybrid. So the energy difference between the most stable radical, sorry, most stable uh, canonical versus hybrid. How much is the difference? That is called as resonance energy. So resonance energy is equal to, sorry, energy of stable canonical minus energy of hybrid form. Done? So that is the resonance energy. Now, usually while writing the resonance energy, you know that this is a negative energy part. So most stable canonical, which means it has highest potential energy, and least will be hybrid, which has the lowest potential energy. So the difference will always come out to be negative. Okay, so this is the released energy, so it will always remain negative. So from here, what we can say, higher the resonance energy value, higher the resonance energy value, okay, more stable the compound. Now, just quickly go through the resonance energy values in all the cases, starting with benzene, naphthalene, anthracene, phenanthrene, pyridine, thiophene, pyrrole, furan, and biphenyl. The name of the last one is biphenyl. And everybody, there is reasoning for all of them, but I think right now your emphasis should be about and just comparing the order. I'll give you one small briefing though. Have you noticed something odd between benzene, naphthalene, and anthracene? You notice more the number of rings are getting fused. Okay. The expected value of the naphthalene should be double the resonance energy of benzene, correct? Which means around minus 300 kilojoules. But how much amount of energy released? Only is minus 250. Why is it not able to release a lot of energy like one benzene ring? Because here it is equivalent to saying two benzene rings. But we learned that in naphthalene, we will not get both the rings contributing equally at the same time. You may have noticed that this one is being more stable canonical, but these two are also contributing. These two are also contributing here. Hence, we can say in the case of fused rings, more the number of rings getting fused, lesser will be the resonance energy per ring. Overall resonance energy will be always high, but per ring resonance energy will be more for benzene than naphthalene than anthracene. Now, only between anthracene and phenanthrene, if you compare, like between anthracene and phenanthrene, which one is being more, which has more resonance energy, then definitely phenanthrene will have more because it's, if you compare the resonating structures, right, between anthracene and phenanthrene, phenanthrene will have more number of benzenoid structures that you can write and learn. Here I have given it. Okay. So phenanthrene versus anthracene. Which one has more resonance energy? How do we define? The first five structures are for phenanthrene. The next four structures are for anthracene. Correct? I think the skeleton is already given to you. I would suggest all of you fill along with me how to write the resonating structures of these two. Because this has been an integer type question always asked, that how many resonating structures we have, and within the resonating structures which are more stable resonating structures. So let's start with the first one, anthracene here. So if you compare the anthracene part, we can see 1, 2, 3, 4, 5, 6, 7. These are the number of pi bond. Let us call this compound as 1. See the second one. Now you'll start slightly changing the rotational form here. So I can get double bond, double bond, double bond, and double bond here with a double bond here. And then this is the way we can write. Likewise, we can also have double bond, double bond, and double bond here, like a benzene form. Then a double bond here, like this. Okay. Next one. Like this, and another two pi bonds at this extreme. Likewise, I can have three pi bonds here, one pi bond here. Right. So these are all the forms. The first one, the second one, so 1 to 5 resonating structures are clear. Now notice when it comes to anthracene, what are things we can write down? Check. First one, we can write this as pi, pi, and another pi here, and that pi bond will be contributing here. So we can say this as P, and these are number of pi bonds. Let us call this as Q. Likewise, we can have on the other side also. Let's call this as R. And lastly, these three are the factors. Now notice one thing very carefully, in the first 1 to 5 cases also, which of them have complete benzene ring form? You can see this one is complete benzene ring, this one is complete benzene ring, this one is complete benzene. So that's why you can see this one has, maximum amount of benzenoid structures. Next. Here you can see this one has a benzenoid structure, and this one has a benzenoid structure. Two benzenoid structures. Here we can have benzenoid structure, and here we have one benzenoid structure. So three. I mean, total number of benzenoid forms are two. And here you can see there is only one benzenoid form. Here we have one benzenoid form here and one benzenoid form here. Got it? So out of all these five, everybody, so which one is the most contributing from phenanthrene? This one. This is most participating for phenanthrene. So this is the phenanthrene, and here this is anthracene. Now in the case of anthracene here, you can see this is a resonating benzenoid form, this is benzenoid form. While here only one benzenoid form. Here also only one benzenoid form. And here we have one benzenoid form. Okay, here also, sorry, here also we have benzenoid form. Hence, you can see P and R are more contributing because it has two benzenoid forms. Q and S. PQRS. P and S are having only one benzenoid form, so that there is less stability. So I think you should be able to figure out what about resonance energy here now. Now, if the ring is completely isolated, like these two biphenyls are isolated, the resonance energy will be almost the double that of benzene form. Finished. Now, quickly compare the resonance energy. Between A and B, both have benzenoid forms, but along with the benzenoid form, there is an outside pi bond which can be involved through resonance. That going to increase the resonance energy. So B is greater than A. Next, between A, B, C, D, we just learned that resonance energy is highest for more number of rings. So D, C, and then between these two here, both of them are pi bonds. But have you noticed biphenyl has almost close to 300? This one minus 290. So while naphthalene has around minus 250. So we can say definitely E is greater than B is greater than A. Next one is ring energy per ring. Per ring, how many we have? So you can see one here. For one benzene ring will be A greater than E, and thereafter we can have this as D, then we have C, then B. So this is the finished. This is the resonance energy per ring. See the next one, A, B, C. How do we figure out resonance energy? Now here is the interesting part. OH carries a lone pair, so that can make a resonance here. NH2 carries a lone pair, so that can make resonance 2. Now, whichever increases the benzene ring density, on benzene ring electron density is increasing, that will always show more resonance energy. So hence we can say C, which has lone pair in conjugation with the pi bonds. So hence C is greater than B, then A. So this will be the resonance energy part. Please check about fourth one between A, B, C, which one has more resonance energy. Simple reason. This has fused rings. This is isolated rings. This is only one ring. Hence, B greater than A greater than C. I guess all of you got that. Right. I'll be uploading one sheet on resonance energy today. Okay. So if you can complete that questions only related to resonance, I think you will get enough idea about how to deal with the questions in generally from resonance energy. Now, the next concept is about hyperconjugation. Hyperconjugation, which is also called as no bond resonance, Baker-Nathan effect, or sigma pi conjugation. These are all the alternative names given to hyperconjugation. In fact, there are mainly four types, but the first three are most important ones. The one is sigma p empty orbital conjugation, generally observed in carbocations. Next, sigma pi star empty conjugation. Pi star empty orbital should be present in which the sigma is making a bond. So that is observed usually in double bonded carbons. Next, sigma and p, which is half filled. P is half filled here. That conjugation generally observed in C. I mean radicals. So what is a condition? Condition must be there should be at least one alpha hydrogen, you know, uh, one hydrogen on sp3 carbon only, and that could be at alpha, gamma, epsilon position like this. So alpha, gamma, and epsilon. At any of these positions, right, we can be able to figure out hybridization, hyperconjugation can be present. Correct. Considering that epsilon and gamma if you get a positive charge or radical form, it must be resonance stabilized. That is more important. Okay, so check. First case, hyperconjugation in carbocations. How does it operate? So, so you notice that carbocation, what type of conjugation takes place? Sigma and p empty orbital. Sigma p empty orbital. What does that mean? How do we need to compare hyperconjugation? Let's see. Suppose this I want all of you to write and learn. Check. If you have hydrogen connected to carbon three times, and then we have CH2. So CH2 means we have hydrogen, and then we have empty orbital with positive charge on it. Correct. Let us say this is hydrogen at, I'm labeling them as ABC. And then what can we do? If you break this bond here and try to achieve carbon minus. So how does this happen? Now notice why it has to break this bond. See, the reason is simple. On breaking that, the adjacent carbon will gain negative charge. Negative positive will make it uh, double bond formation. So that's what you'll notice here. Carbon having two hydrogens here like this, and now it has almost lost the hydrogen bond here. With hydrogen, and because of which now the carbon possesses two electrons in here, and that if you connect it with the next carbon having two hydrogens and one empty orbital, right? So because it has empty orbital, so you can notice that so I can say that here this pi bond and this pi bond, pi orbitals are parallel to each other. Hence, they can start showcasing a pi bond formation in this case. And that's how you will see we will have carbon with two hydrogens, but it also has one hydrogen lost temporarily as H plus ions, making a double bond carbon, double bonded with CH2 here. So you can see this position, there is no bond. That's why it is called no bond resonance also. Okay. Now these two hydrogens, I can write it this way as H and H. You can see this is B, C, and here we have H plus A. So between carbon hydrogen, there is no bond formation. Like this, can you see how many total number of structures we can have? So here, once I can do it with A, once I can do it with B, once I can do it with C positioned hydrogen. So just like how we write the canonical structures, now this is the hyperconjugated structures. Therefore, we see three alpha hydrogens. Hence we have more stability. So you can see we have one, two, three. So three alpha hydrogens. So accordingly, you can notice the stability. How does the hybrid look like here? So in the case of hybrid, you will see we have H connected with carbon, connected with hydrogen, and then connected with CH2. Now, these bonds have become relatively weaker. I'm writing that in terms of hybrid. Like this. If you are able to do that, I mean, if you're able to get this kind of structure, that means you will have more number of alpha hydrogens, signifies more is the stability. Hence, I guess in the carbocation, everybody is clear with that. So you can see what is the type of overlapping we are doing. The type of overlapping here is sigma making a bond with empty p orbitals. All good? So you can see more the number of alpha hydrogens, more is the stability. Okay. Now you notice how many number of alpha hydrogens are present in all the cases. First write all the alpha hydrogens, everybody. Add everyone. Just compare what are the number of alpha hydrogens. The first case is 0. There is no alpha carbon. Here we have 3, 6, 9, 0. And alpha hydrogen here we have 3, 0. Why 0? Although it has an alpha hydrogen, they are on sp2 carbon. sp2 carbon is irrelevant. We need only sp3 carbon. Here we have 2. Here we have 4. Right side, this one is also alpha. This one is also alpha. So that makes it 4 alpha hydrogens. And lastly here, alpha hydrogen is equal to 3. Sorry, in this case it is only 2. This is the alpha carbon. So with respect to positive charge, we have only these 2 alpha hydrogens. Generally, if you are comparing the stability, always use these 3 factors. First, give the highest priority to resonance. Next, priority to hyperconjugation. And then only the third factor is inductive effect. Okay. So everybody, please try these 2 questions. Try to figure out what is the stability order. You can write the answer on the chat box. In A option, we have 2. This is alpha position. So first let me assign the alpha here. Alpha, alpha. Here it is alpha, alpha and alpha. Alpha, alpha and alpha here and alpha. So only E does not have any alpha carbon. Rest of them has alpha carbon along with some hydrogens. So how many hydrogens we have? 2. Here we have 6. Here we have 8. Correct. Here we have 9. Here we have 0. Here we have 3. Radhika, please check again. Beta. Did you get that now? How many
Yes,
alpha hydrogens we have?
sir, I also sent you my answer.
Yes, beta, I've checked it. Yeah. So this is one order you sent, right? First one.
Yes, so it's
Yeah.
the answer to the first question.
Yeah. Yeah. Check. So yes, based on that, we can get D, which is more stable, then C, then B, right? Then F, then A, then E. Correct, but what about the second one? Everybody, first figure out how many alpha hydrogens we have. This is alpha, 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 and alpha. Alpha here, and that's it. There is no alpha there. Okay. So based on that, now alpha hydrogen contribution, how much we have? Contribution only one hydrogen here. Here we have 8. Here we have 4. Here we have 1. And here we have 1. Alpha hydrogen, here we have only 1. And here 0. This is the one we have. But you got to understand one thing. So if at all you're checking the stability, here, especially in the case E and F, you need to check, is there any resonance effect observed? In F, have you noticed that there is a resonance effect also? Because this double bond can shift here. That means the positive charge can be resonance stabilized. If it is resonance stabilized, that is always going to be the high priority for us. So due to resonance stability, which is the highest
Let me,
stability
sir.
here, F. Yes, beta.
Sir, in the the D figure, shouldn't the number of alpha hydrogens be 2?
Yeah, 2. Sorry. This is 2. Okay. So first we got it as F, which is due to resonance. This is not to do with hyperconjugation. Next, now when there is no resonance, then you have to compare hyperconjugation. Based on hyperconjugation, we can see B is more than C is more than D. Now between E and A, you notice that E also has resonance stability. E also has resonance stability. F also has resonance stability. Sorry, E does not have any resonance stability. My mistake. So E does not have any resonance stability here. So here the pi bond is present here and alpha is present here at this position. So therefore, based on that, if you compare E, of course, this double bond is relatively withdrawing. So it is not going to be stabilizing inductive effect wise. Okay, as much as what you get it from D. D, everything is donating only. So here everything is donating part. While on this position here, you can see this methyl is slightly withdrawing. So in that sense, on the alpha position here, there is more donating nature. Here there is less donating nature, slightly withdrawing nature also present. Therefore, D greater than E, correct? And if you compare D, A and E, if you compare these three, now D is definitely more. Between A and E, you can say A has slightly better edge because it has more donating group. E has slightly withdrawing group because of double bond. So A greater than E. So this should be the order of stability. Okay. Always check out first resonance effect. Second, uh, number of alpha hydrogens. That is comparing hyperconjugation. Third, only if the alpha hydrogens are same, like in this case A and E, then you check out whether there is inductive effect on that position or not. So more the inductive effect, uh, more plus I effect, more is the stability. More minus I effect, less is the stability. I guess this part is clear, everybody.